Welcome to this session. Again, for those who attended Bernard's session, this session nicely complements that. The focus here is going to be on OFI support for accelerators. I'll go over the terminology and the usage later. And as part of that, we have developed a software-hardware framework, a proof of concept using Intel's static extend FPGAs, which validates these extensions, and it runs at 100 gigabits per second. And because the focus is more on the OFI extensions, we are not going to be showing the performance data here. But everything that Bernard said about FPGAs being first-class citizens is equally applicable to our work. So just wanted to thank Bernard for actually giving, for the session to actually follow his session. And I want to acknowledge all my colleagues at Intel. Olivier and Mike have joined, as well as Andre, Patrick, and Sean. So by the way, the proof of concept that we are going to be describing is not an official Intel product. It's a proof of concept at this point in time. Next slide. You can skip the next slide as well, the problem statement, and go to the subsequent slide. Thank you. So I mean, the term network is the computer. I mean, I'm sure everybody has heard that. It was coined by John Gage probably maybe 30 years ago. So the concept is that the network is the focal point of the computation. So the computational resources are like just spread out across this network, and it's the network that binds them all to provide scalable performance. So that's pretty much what that concept refers to, and it's still applicable today. There's no change, and now that accelerators are playing a significant role in compute, along with general purpose CPUs, accelerators have to be tightly integrated with the network communication. So that's going to be key to scalable performance. So this slide shows the trend in terms of supporting this direct network interface to the accelerator, moving beyond providing a network interface to CPU, and then eventually there's going to be tighter integration of CPU, general purpose CPU, accelerator, network interface. So all this boundary is going to be eventually blurred. So it doesn't really matter in the long run as to who would own the network interface, whether it's the CPU or GPU. But the basic concept is that it is going to be it's going to be the building block for this network is the computer usage model. So in any case, exposing these accelerator capabilities that involve networking using standard APIs is extremely important. So before we get into that, I just want to make sure I explain the terminology that we use for the accelerators. So accelerators in this context, in the context of communication, can be classified as, say, inline, which is, some people call it as bump in the wire, where as you are sending and receiving the data, you can actually perform acceleration on the fly. And then the other option is to something called lookaside, where the computation itself perhaps cannot be performed at wire speed. So you would do it separately, and then the outcome of the computation can then be used to send across the wire. And there you could have a discrete model where it could be a GPU, or it could have something which is integrated on the NIC itself, where it's highly programmable. So pretty much it's something which is standalone. So that's the basic idea. So the next slide clarifies it in somewhat greater detail. So here we are again talking about these different types of accelerators. So what this the slide shows is the concept of what is inline, what is lookaside, and how it can be invoked both locally as well as in a remote sense. So as I mentioned earlier, some compute entity will want to transmit data. So the inline accelerator will be used to perform the compute on the data. So you can think of it as a streaming model. And then there's a lookaside that I mentioned, where the computation is performed, but the data itself, the outcome of the lookaside acceleration, whether it's done by a GPU or whether it's done by something in this SMARTNIC accelerator domain, that data can be directly transmitted through the network port to a target. So that's the basic two accelerator models that we are going to be assuming for the rest of the discussion. Now, this accelerator block can either be invoked locally. In other words, as you are sending and receiving the packets, you may want to perform this acceleration during the course of transmit or possibly during the course of the receive operation. Additionally, you can actually invoke this acceleration remotely. I'd like to call this as a triggered accelerator mode, where the packet ends up triggering that acceleration, and that acceleration could be both an inline acceleration or a lookaside acceleration. So the beauty of this is that this remote mode of acceleration can allow the target to be headless. So which means that you don't really need to have a CPU or an operating system involved here. And actually, it ties nicely with what Bernard mentioned earlier about FPGAs can be serverless and it can be used for hosting some function or microservices. So that's a very good usage model here. There are a lot of interesting things that we can do with this model as well. But the bottom line is that everything looks fine and dandy, but what's the API for exposing these different types of accelerator modes to middleware and applications? And that's where the focus is going to be. So if you could please go to the next slide. So this is a standard picture that has been decorated with some of the additional things that we have done. So this is the standard OFI stack. So what we are talking about here is to use OFI and then extend it for supporting this different type of accelerators, the inline, LOOKASIDE, and to invoke it both locally as well as in a remote fashion. There have been certain additional work that has been done in terms of taking, say, OpenCL, for instance, and then using pipes to go beyond a single node. And in this context, actually, the OpenCL model actually uses FPGAs. It allows kernel pipelining. You can do kernel-to-kernel communication between FPGAs, but it's not really a scalable solution. It's actually a probably more logical to take a network API and then use it for supporting acceleration, which means that you can actually get a true scalable model. So with this approach, then the OFI would have some certain extensions that we are going to be talking about. And there are a couple of ways where it can be exposed to the upper layer software. So for instance, as you can see in this picture, there's a lot of middleware which uses OFI. So the middleware themselves can transparently use these acceleration functions without actually exposing it to the upper layer software, the application, for instance. So the applications themselves will not be seeing these accelerators, but the middleware can make use of it. So there are a lot of areas in MPI, for instance, or SHMEM, for instance, where it could benefit from certain accelerator support, and that's part of our pathfinding work that's ongoing. Now, there's also an option where the application themselves can directly use OFI. So that's a way where you can actually make use of these extensions directly and then get the full benefit of the underlying accelerator model. So overall, even though we have done this in the context of FPGAs, the work is completely agnostic to FPGAs. Just like what Bernard mentioned about the stack, pretty much abstracting away the FPGA functionality and letting anybody to use the TCP sockets interface. In the same way, the OFI interface provides pretty much the abstraction layer, and under the covers, whether it's an FPGA or whether it's an ASIC, it's completely irrelevant. So that's sort of the takeaway from this slide. So now,
there is a question. The question is, where this is an abstract layer, understood, but is there any performance difference with and without this abstract layer on an FPGA?
The abstract layer is OFI, and then can you hold on to the question? We'll go into the details of the software architecture, and there is a hardware abstraction layer which is below the OFI layer where we can talk about it. So if you could please hold on the question. Unfortunately, I don't have performance data in this presentation because the focus was mostly on the OFI extensions, but I'd be glad to provide the additional data if you're interested. So if you could move to the next slide. So to test this concept out, we as I mentioned, we build a hardware prototype. So this is just to rephrase what I was mentioning earlier. So the hardware vendor specific implementation is what we have done. So we have defined a mechanism by which how to specify the input output acceleration parameters and how to invoke the acceleration, whether you do it locally or whether you do it remotely, and extending the communication framework to support these different types of acceleration functions. And then the API itself is what we're talking about for OFI. So this whole thing is based on this hardware prototyping, which is FPGA based. So if you can go to the next slide. So this prototype that we have developed is a SMARTNIC accelerator integrated framework. It's called COPA, stands for Configurable Network Protocol Accelerator, and as I mentioned earlier in the presentation, it's a POC and not a prod. So the COPA work can be broken into two phases. The first phase provides a baseline model. It provides the standard functionalities like providing RDMA, put the get-based communication, and it provides all the necessary infrastructure where accelerators can be invoked as part of the communication. And then, of course, there's a software support as well as part of it where you use OFI to expose it to the upper layer software, which is like applications or middleware. And the hardware itself is layered upon standard IP Ethernet. The transport is something which we have developed to support this put-get-based communication model, and it supports both reliable and end-to-end unreliable mode of communication. And currently, as I mentioned earlier, we have it working at 100 gigabits per second. And the second phase of this work is to take this infrastructure, take this framework, and then start customizing it depending on the usage that you're targeting. So there are like different customers, different applications that could actually take this and then adapt it and provide the necessary accelerator blocks that are needed, which would make it run faster. So they're not going to be going into that in this discussion. Next slide, please. So this picture provides the different system components that we have in place where COPA is functional. So there are three different types of FPGAs that we support. As you look at the top left, it's a standard PCA attached FPGA where you have currently it's a PCA based interface, but eventually we can move to a CX based interface. So it attaches to a Xeon platform, and the OFI stack here would run on the Xeon, and then the rest of the hardware, transport, accelerator, everything would run on the FPGA itself. So pretty much this is going to be one of the system component. And as you move to the right side, you have an FPGA SoC model where there is no need for a separate Xeon processor which attaches to the FPGA. Instead, we make use of the integrated ARM that's available in a standard static extend FPGA, and that would end up running the OFI stack. So the software stack is, obviously everybody on the call knows that OFI is very portable. Depending on the hardware platform, you pretty much have to write a different provider or change, so have minimal changes to the underlying hardware provider. So we have been able to port it to this platform as well. And so from a usage point of view, it's no different. The same application can run both on the Xeon as well as on the FPGA SoC with absolutely no change, and we have validated it. Then there is something called a headless node, which is where there is really no need for running a OFI stack. So here is the case where you can actually invoke the accelerator, like trigger the accelerator through the network, and then get the operation done on this remote FPGA. So this as we saw in the earlier talk, this conforms to this serverless function or possibly hosting microservices model here. And as I mentioned earlier, all this works on a standard 100 gigabit Ethernet. So we have used a 100 gigabit Ethernet switch here, no change whatsoever. And then it uses standard IP UDP based protocol. And the only part is that what we have layered on top of it, layered on top of IP to provide our custom transport. Next slide. So this is a very high level overview of the hardware stack that we have put in place. So you can think of this hardware architecture as a combination of a NIC as well as accelerators integrated onto the FPGA. So currently, as the picture shows, inline accelerator blocks can be invoked directly on both transmit and receive operation. There's also LOOKASIDE accelerator blocks that we have implemented. You can think of it as a proxy for, say, a discrete GPU, or whether it's a integrated accelerator in a SMARTNIC, it doesn't matter. But it serves the purpose of providing this LOOKASIDE accelerator blocks, and that can be then invoked. Currently, it can be invoked independently. So there's a little bit of software help that we have where software ends up posting it into the LOOKASIDE accelerator queues, and then the result of that operation is still kept inside the FPGA memory, and then it's directly transmitted over the network. So we will discuss some of the OFI extensions for inline and LOOKASIDE invocation later. So that's sort of the basic idea. I don't want to get into this hardware architecture in detail, but this should give you a good idea of what is there inside the hardware stack. So let me move on to the overview of the software stack, and hopefully this would answer the other question. If not, we can revisit it. If you could please go to the next slide. So this one gives a summary of the different components of the software stack. So I already talked about the FPGA hardware piece of the solution. So moving beyond it from a usage point of view, it acts like a standard device. So you have a COPA device driver, which does the standard functions which a normal device driver would do, including mapping CSRs and command queues and whatnot. So there's a lot of end-to-end reliability connection table setup also that the device driver does. So by the way, this is not going to be on the critical path. So once all the establishment and the setup is done, the upper layer software can directly use it and have a kernel bypass. Now there is a hardware abstraction layer called library COPA hardware or libchw that we have layered on top of this device driver. And this is the main system programming interface. So the OFI provides a next level of abstraction that allows all the middleware to run, but internally we have our own abstraction layer. This is as close as it can get to the hardware, and everything that OFI ends up, OFI ends up invoking this the COPA hardware library for all its functions. So we have done some measurements that I'm not showing in this presentation, where the difference between COPA hardware library and the OFI provider for COPA, there is a bit of a difference, but it is not it's not significant. So pretty much we are able to capture most of the performance at the OFI layer itself. So then going beyond the OFI provider for COPA pretty much is the interface to the external world, which completely shields all the idiosyncrasies of the underlying hardware and the underlying provider, functionalities. And every application and middleware ends up using this OFI interface. And then, of course, finally, the applications middleware is the top layer, and they pretty much are completely blind or agnostic to what the underlying hardware is. So this is the overview of the full stack. Does that answer the question that was raised earlier?
Yeah, the question was with this abstract layer, if there is an FPGA underneath, is there a performance difference that you can talk about?
Yeah, the fact that there's an FPGA underneath, or whether it's an ASIC underneath, is completely hidden, unless I'm misunderstanding the question. So the low-level library, the hardware library, is the window to this underlying hardware device. So in terms of programmability, in terms of the performance, you're not going to see more improvements by programming directly and using the FPGA interface directly. So in terms of the comparison, there's really no standard API for us to use the FPGA hardware at this point in time, where we can actually have communication also as part of the interface.
Okay, makes sense. Thank you, Venkata. If there are other questions from the participants, please feel free to submit those through the panel or even raise your hand. I do want to keep this interactive, so yep, looking forward to those. Thank you.
Sure. Thank you. So this should give you like a quick, or at least a reasonable high-level overview of the framework itself, of what we are doing. In the interest of time, I had to rush through everything, but all the slides will be distributed, so you can look at it at your leisure. So I want to spend the rest of the time touching upon some of the OFI extensions that we have put in place, and there are also some backup slides that have some examples. And if there is some time left, I may be able to cover them. But again, if not, the slides will be distributed and you can take a look at it. Any questions so far before we jump into the details of the extension, OFI extensions? Thank you. So then you can go to the next slide, Lydia. So one of the important contributions of our work is that we currently actually have a reasonably fully featured OFI provider in place. So we have been able to run a specific middleware. Currently, we have deployed it, and then we are in the process of actually making sure MPI and SHMEM also is functional. There are some little bit of changes that we need, but it's work in progress, and I think we should be able to get that also completed. So once we have that, we should be able to open up this interface for any arbitrary MPI or SHMEM applications. And one of the key message here is that there were no new OFI functions that were added to this work. So everything was based on existing fields. Everything uses the existing flags or some of the parameters, and all we did was to extend the semantics to support this inline and lookaside acceleration model. And as part of it, we did define some new flags, but that again can be overlaid as part of the existing flags. Of course, whatever we are positioning out here is not considered official OFI support. It's our own version of how potentially OFI could be extended. So treat this as such, treat this as like a temporary enhancements until it becomes part of official OFI. And again, we work closely with some of the OFI folks, including Sean, on this effort. So let's see where that leads to. But as of now, you can think of it as an internal prototype. And currently, it supports all possible interfaces, right from messaging and RMA and so on. So I'll not get into those details right now. But the key takeaway is that no new OFI functions. Everything uses existing OFI parameters, and we have just extended the semantics. Next slide, please. So this one is about how we went about providing this acceleration support. So for acceleration support, there are two ways we can actually do it. One is we can enable it on a per operation basis. The second option is we can enable it on a per endpoint basis. So if I have some time, I can go into the backup slides where you can see as part of, for instance, the FI write operation, there is a context field that's part of standard OFI, which we actually use and overload it and provide some of the acceleration parameters. So once we associate an endpoint as being acceleration capable, then essentially we end up specifying the specific values in terms of the acceleration flags. And these acceleration flags, as I mentioned earlier, can be set for each endpoint object, and then you can essentially invoke it for the different data moment operation. So there are certain couple of OFI functions like FI write message and FI read message that is mentioned here, where you don't necessarily have to enable it on an endpoint basis. So it actually has this additional parameter where you can actually invoke it on a per operation basis. So that option is also available. So next slide. The accelerator outputs itself, the data field that we are using is this data as part of the completion queue data entry structure. And currently, this is actually used at the receive side in OFI. So what we have done is we are also using it at the send side. So there are two ways it can be used on the send. One is like when you invoke an acceleration operation, the result of the operation can be readily be made available to the sender. So the completion data on the sender side can be immediately be posted, and then you may also want to get a completion once the full end-to-end reliability is completed and the complete operation has been successfully flagged. So there's a possibility of getting two completion operations on the transmit side. And in addition, of course, on the receive side, you can still get a completion operation as part of the standard receive side completion, and the data is going to be posted along with the necessary fields on the receive side as well. So what we are doing is we are overloading this or extending the semantics of this data field to contain the accelerator result. Next slide, please. This one is on the LOOKASIDE acceleration, and as I alluded earlier, it's independently invoked. The standard FI write, FI read, everything contains all the necessary information for invoking this accelerator along with the necessary remote destination parameters. Our current hardware implementation doesn't fully support this model. So what we have done is there's a little bit of additional work that is needed at the software level. So the way software currently works is, if you recall the hardware overview slide, we have two separate command queues. Software would post it into the accelerator command queue first, along with the type of accelerator operation that needs to be invoked. And then once the operation is completed, then it would post a completion like what I mentioned in the previous slide. And then the software would see the completion and post the command into the transmit command queue. Notice that the data itself will still reside in this domain. It will not be sloshing back and forth between the accelerator domain and the CPU domain. So all software does is does a sort of a management where it actually ends up sending the same pointer that is residing inside the accelerator domain and tell the transmit part of it to send the data out. Sometime in the future, we'll integrate it to a point where software doesn't have to do the second work, where it actually has to invoke the LOOKASIDE accelerator separately, and then also it needs to invoke the transmit operation separately. So that's something which will be completed in the future. So this gives you a sort of a good overview, and if time permits, I think I might have like a couple of extra minutes. So if you don't mind going maybe perhaps to the last slide before we go to slide 15, I can just the last slide as in the back. Okay, maybe if you can skip like 3 more slides. Just want to show the one more slide, please. One more. Yeah, thanks. So this is this gives you a better context of how we are using it. So I mentioned earlier, for instance, the FI write operation itself, how we are overloading the context. So here you can see the context itself is again a user-defined context, and the context is overloaded by specifying the type of accelerator function that needs to be invoked. So if you look up, you can see that the specific type of accelerator that is currently being invoked in this operation is a CRC operation. And then we are providing some initial input to the accelerator functions. It's just some seed value that we are providing. And then the invocation, the FI write operation itself has not been changed at all. So it's just the same as what it's being done right now. And inside the COPA provider and the lib hardware and the COPA hardware will end up taking care of how to interpret this context and invoking the specific accelerator operation. So this should give you a sort of illustrate how we are using it in terms of using it for some of our invocation models. So I think I'll stop here and then go back to the closing remarks in like 3 slides earlier, and then I can wait for more questions. Thank you. So the next one, please. Thanks. So as we discussed in this presentation, traditional accelerator APIs like OpenCL are not really meant to scale across multiple nodes, and they're not architected to support networking. So OFI is the best bet here. So what we have done is we have taken OFI and used that OFI and provided minimal extensions, and then I've built a provider that exposes these accelerator capabilities. And we think we have actually validated it on a fully functional COPA FPGA cluster. So we have validated both inline and LOOKASIDE accelerator implications, and we have actually achieved full wire speed. We have been able to run at 100 gigabits per second in terms of doing both the network transmit receive operation as well as invoking the accelerator, inline accelerator on the fly. And so overall, this work has actually proved that OFI can indeed provide a unified interface for both acceleration as well as networking. So I'll stop here and then open up the floor for additional questions. And I also have my colleagues, Olivier and Mike Blocksome on the call. So if there are some other questions, they can also answer your questions. Thank you.
Thank you, Venkata. Let's just give a minute for questions to come in. In the meantime, I'm going to open the mic for Michael and Olivier in case they would like to add any comments. All right, so there is Paul Gruen who will be, I guess, chiming in with some comments. Paul, go ahead, try to unmute and speak. Try again.
There, can you hear me?
Yes, I can hear you, Paul.
Thank you. On slide 49, you discussed the headless node, which is an intriguing concept. The idea of a node that has really essentially no software behind it. But doesn't it, how far along are you in your thinking with that? It seems like there'd be a raft of issues that you would need to overcome. For example, somebody on the network somewhere has to be able to discover that resource and allocate it to consumers somewhere. It seems like you would have to do things like the moral equivalent of extending an FI get info kind of an operation across the fabric to discover this thing. So what's your thinking about the headless node? How far along is the thinking there?
At this point in time, Mike can chip in later after I'm done. At this point in time, we have validated it as if it's not a multi-tenant environment. So what we have currently put in place is that a specific application that is running on the entire cluster can invoke that accelerator on the remote node. So in terms of security in terms of partitioning. That would be our next step. And yeah, that's actually a very important question, and that we intend to address in the future.
But even in the single consumer environment, that consumer would have to be able to discover the fact this accelerator existed across the fabric somehow, and it would have to be able to configure it some way, wouldn't it?
Currently, for a specific application, there are certain set of services that are essential for that particular application. So we are currently assuming that it's already pre-configured, and in terms of the availability of these different type of accelerator services, we are configuring it in a static manner. But eventually, we need to have, along the lines of what Bernard mentioned, in terms of having a manager, a resource manager, which can actually discover what type of services are available and then list it all out in a way where the management software can understand it and then provide it as part of the capabilities at the fabric level. All this has not yet been done yet.
Okay, and to go hand in hand with that, then there has to be at least enough intelligence on that headless node to be able to receive the queries from that manager wherever it is and respond to them, right? That's what you're thinking.
Correct. It's a target, so it can understand the packets coming in. It can interpret what the packet says, and then it can invoke the operation then and there. And additionally, when I say a headless node, this is not to exclude the possibility of having a small management CPU, which can do all the necessary initialization. In fact, one of the deployments that we have done, again, as a POC, is to actually have a management CPU. What this is conveying is that it can act like a sort of a dumb target. It won't be initiating the operation using OFI running on the headless node, but it can respond to the information. But at the same time, it can participate in terms of the management setup.
Okay, makes sense. You got to be careful there that you want that to be a low capability CPU in order to discourage people from begin to stack the natural inclination.
Correct, indeed. Yes, I agree. Yes, that's definitely the case.
Yeah, we're thinking of some very small soft core processor to do that. Like we already have our RDMA hardware protocol implemented on the FPGA. We just need something like that, configure the connection table on that, monitor the connection. So it can be very, very low power, like 8 bits of core processor could even do it for us. Okay.
Another distinction is that one of the earlier slides, Venkata had the SOC diagram, and that's sort of headless, right? But we still have a processor and we're still running OFI software, but it would be configured so that it could be the target of acceleration. I think that's the key point. So when it pulls a packet off of the fabric, it would do an acceleration right there without invoking any kind of software and then return a response. But there would still be OFI and software running and kind of setting things up. So that would be like a step in between a fully autonomous, fully, only hardware, no processors, kind of a headless node. So.
Right, and in the fullness of time, you can imagine some minor extensions to OFI, the lid fabric, on the consumer side to help him be able to discover, the resource which used to be local to his node and which is now located across the fabric. Again, the analogy that occurs to me is some sort of a, FI get info across the fabric function, and I can see where that might be a useful thing sometime in the future, depending on how this all works out.
Okay. In interest of time, I am going to have you guys take any questions offline. I'm going to go to the next session, looks like it's 9:20, so we are eating into break. We may get a shorter break than usual. Guessing that is okay, given we are all very close to our, I guess, needs to take a break, the places where we need to go. All right, so the next speaker